It's a bit, the two screens are messy. Working?
Yes.
All right. Good evening, everyone. Sorry for the delay. I had to send out a lot of apologies. Today we'll have our lecture on traffic. The pedestrian lecture will be done next week. We've gone through all the slide sets again. And we'll start with the one-dimensional collective dynamics. And next week, then we'll focus on two-dimensional interactions of people. And so today we'll focus on empirical findings. We'll talk about time-dependent phenomena, traffic flow modeling, the so-called phase diagram of congested traffic states, how to overcome freeway congestion, and then we'll enter the subject of traffic light control. Now, I'd like to start with a discussion, and so I'd like to encourage you basically to open up your mic and to say, what do you already know about traffic? So let's do a little brainstorming if you don't mind. You can also open your video if you like, but you don't have to. Anybody wants to go first? Sachit, perhaps?
Well, I don't know where to start. So, because, I'm originally from India. So for me, traffic has always been a pain, to be like in very, limited words, I would say, because, yeah, there's a lot of congestion and yeah, like, for example, here in Switzerland, it's usually most of the time, in Zurich, it's fine, but sometimes I see my colleagues and friends telling me, oh, it's really crowded and it's like a traffic jam. And then sometimes I compare it with what I've seen and this, and I feel there's so much difference, and how it changes based on location and area. And yeah, that is like my first impression of traffic, to be honest.
All right, thank you, Sachit. Anybody else wants to add anything?
Well, I can say that every time we try to avoid it, somehow, like using a navigator, Google Maps, something like that.
Okay, and is that always successful, using all the modern technology, or are we just entering another traffic jam?
No, I don't think it's really successful. I mean, sometimes you just change the street, but there's traffic also in the other street that's not like pointed out in the app or what we're using to go from a place to another.
All right. Anybody else would like to contribute?
I think a lot of people nowadays rely on Google Maps, and Google Maps has this function, or has this kind of inbuilt algorithm of avoiding traffic jams. But at the same time, depending on how many people use it, it might unintentionally create another traffic jam by a lot of people using, for example, the side roads.
Exactly, yeah. That was what I was thinking about when I was asking. Any other points? Actually, I have another slide. Yes, please go ahead.
I think there's a whole field dedicated to trying to simulate it as best as possible.
All
to
right.
then optimize roads, accordingly.
Good. This is what we will talk about today, in fact. So what else might be interesting? I haven't heard anybody talk about autonomous vehicles, for example. Is that of any interest?
I would assume that if everybody would have an autonomous vehicle, that we will have way less congestions, because basically the car would not have this error margin of stopping randomly or accelerating too much. But I also assume that for like the perfect flow on the roads, each of the cars should be like autonomous driving and not a mix-up of human drivers and autonomous cars. But that's just my point of view.
Okay, so there will be a day X where everyone basically invalidates the driving license and cars take over. Is that the plan? And I mean, if you don't want to have a mixture of robot cars and drivers, or cars driven by drivers, then we need to have a day X, right?
Well, at least from the model point of view, definitely.
Okay, who thinks we should do it this way? Or do you think robots should be able to adjust to people and no opinions?
Well, there's a huge debate about it, like how good the autonomous vehicles would be, or how much it would improve the life in general, but still I think, yeah, personally I wouldn't want, like to give total control to robots, because yeah, with all the digital tech and tools, it's so easy to hack things these days. So I just imagine, a scenario where a central, control station, like it is hacked, so everything would be kind of controlled by someone, and that could really lead to chaos.
Well, yeah, sounds like a scare scenario almost. Who's worried about hacking autonomous cars? I haven't been too worried about it. I mean, I'm basically waiting for years now to have the car pick me up in front of the door and bring me wherever I want, but it's not yet that there. Okay, so that was just kind of the wake up part of the lecture, and now we're basically entering the structured part. And traffic is interesting because it behaves counterintuitively. So over here, for example, you see a freeway with an on-ramp, and you see that we have smooth traffic flow along the road until there is actually a reduction in the density, and that reduction produces a perturbation in traffic flow which already has passed the location of the on-ramp where the cars are getting in, and then it returns. So there's a boomerang effect. And when it again arrives at the location of the on-ramp, we find a breakdown of traffic flow suddenly, such that there's a queue of vehicles forming, but also there's a stop and go dynamics. So nothing has changed apart from the density was reduced for some time. Did you think this would cause a traffic jam? But it actually can under certain kind of conditions. We'll talk about congestion patterns. We'll talk about the analytical theory of traffic flows shortly. We'll talk about self-driving cars or autonomous vehicles. We'll talk about traffic light control. And now we'll start with the empirical findings. And of course, you can stop me anytime to ask questions or make comments, right? This is very welcome. You can find some of that material in my review paper and also in my book, but of course there's a lot more literature from other people too. Now, when it comes to these kind of things, you can find that in many publications. This is the speed density relationship. That means how the average speed changes as the density of vehicles increases. And as you can see in the beginning at very low densities, there's almost no change in the speed because cars can just overtake each other. This is for a freeway with a speed limit of 120 kilometers an hour. And then, however, from say 10, 20 vehicles per kilometer in lane, we see that the speed actually drops quite dramatically. And then eventually it goes down, down, down until 0. And a related graph, which is at least as important, is the flow density relationship. The flow is density times average speed. So it has something to do with how many cars are being served per unit time. And you can see it starts linearly, but then there's a maximum somewhere around 30 vehicles per kilometer in lane. And then the flow goes down, and at very high densities, it can reach a value of 0, right? This is sometimes approximated by what they call the fundamental diagram, and that summarizes a lot of features of traffic flow. However, much more interesting are, of course, the dynamical phenomena. And here you see a trajectory. That means how the flow changes with the density over time. And then you can see for the same density, you could have different values of the flow. So there's some hysteresis effect, you can say. And in particular, at large densities, there's not any more clear relationship of the data to the flow density curve that is shown in a dashed way over here. But somehow there is instability, we could say. And in fact, this is reflected also in the behavior of single vehicles. So what you see over here is the distance over the relative velocity for a car as compared to the car in front. And you can clearly see these oscillatory patterns. So there's no stabilization in the sense that the car would follow with a relative velocity of 0 with a fixed distance. Rather, there are some oscillations, as I already said. And that, of course, has to do with the limits of the perception capacity of the driver, and also with difficulties to control the car exactly. I mean, doing good enough, obviously, but these kind of oscillations happen in particular when the density goes beyond a certain threshold. And particularly in congested situations. And so what you see over here is that once that happens, the time gap is actually increasing on average when traffic gets congested. And as the time gap is increasing, the flow is reduced. Why do we need the higher time gaps? Well, basically, in the unstable regime, in the congested area, basically, you need to have more safety distance in order to be sure that there will not be an accident. So related to this increase of the time gap, you see that the flow is actually dropping. We're talking about a capacity drop over here. And this is a very important finding, because basically when traffic reaches the maximum flow, it turns out that the flow becomes unstable. And then we have that capacity drop such that the same road, say the freeway, would only process less vehicles per hour and lane than it could potentially process in free traffic flow. So the road loses capacity, and it loses capacity just when we need it most, when there is a rush hour. And this is a very important finding, because it basically says that we need to delay the capacity drop as much as possible. Actually, we need to avoid it. And then in this way, you can reduce congestion and increase travel times a lot. We'll later learn what actually triggers those capacity drops. In fact, it's possible to delay them. And that is where technology comes in. Now, also the speed, because of that speed density relationship, is dropping a lot when the flow goes down. During the rush hour, this is here between 7:30 and 9:30 approximately. And you can clearly see that as the speed goes down, the density goes up, and the other way around. But importantly, once traffic flow breaks down, it stays broken down for a long time, actually here for 2 hours. So, you know, once you have basically messed up with free traffic flow, it cannot be repaired for a long time. Any questions so far? Here's actually one more plot, which is also important, which adds the information that the breakdown of free traffic flow is not a deterministic thing. There's some probability that it happens. The probability that it happens soon is greater when the flow is high. When the flow is not that high, it takes longer for the traffic flow to break down. I think that makes sense, right? But that also adds some unpredictability of the breakdown events. It really depends on details of the traffic flow, as we'll see later on. Now, personally, I think the most interesting part of traffic flow is that there's an emergence of congestion patterns. Right? Nobody wants traffic jams. Everyone gets a driver's license, so everyone has a good driving education. Let's assume also that everyone has a good car. Visibility is good. The car is well and easy to control. And still, in a situation like this, where everyone is just supposed to drive in a circle in a steady way, this most likely will fail. Because when the density is above a certain threshold, then small variations in the speed will actually amplify. The next car will respond to that, but with some delay, and in order to compensate for that delay, the car will brake a little bit harder, the next one even harder, and thereby basically we have not only a domino effect, but also an amplification effect. And in the end, the traffic flow breaks down, cars get stopped, even though nobody wants this to happen. We call this systemic instability. And a lot of problems in the world that we still have are of this nature, that perhaps the single component is quite well controllable, but once the elements interact with each other, there is a collective dynamics that sets in, which could be pretty uncontrollable. Now, even if you have, say, mass surveillance data about what's going on, you would see that undesired phenomenon happening, but it doesn't mean that you could actually prevent it from happening. Now here, you can see some empirical data of so-called trajectories. So this is car following data. For each car, there is a line. Distance is shown over time. That means the slope corresponds to the speed. And you can see that suddenly a stop wave emerges. And that means a so-called phantom traffic jam comes about. And this is something that people have been very much interested in, and many mathematical models have been developed for that. But in reality, things are a lot more complicated, actually. And here you see two congestion patterns that we have actually recorded along a freeway. And it turns out that is really very difficult to understand what's going on there. So you see basically the inverse velocity along the road in the course of time. And to be honest with you, if we had started with these plots, I would probably have left the field and done something else instead, because this looks very complicated, hopeless almost to model. But at that time, we already had developed quite a few models for what we thought would describe traffic flow. And now we had to basically use these models to understand those patterns. Now, what you need to know is the road is inhomogeneous. So there are kind of on-ramps, there could be gradients, there could be changes in the number of lanes, and that has something to do with the patterns that occur over here. Also, on the right picture, there has been an accident, actually. So lanes of the road were closed down. Now, what we've decided to do, and that was actually quite successful, was that we were trying to decompose those complex patterns into elementary traffic patterns. Now, in a very similar way as physicists try to understand matter from elementary particles. And one of those elementary patterns is what we call pinned localized clusters. That means this is a higher density area which does not move along the freeway. It could be something before, which we call the boomerang effect. Over here, let me get a laser pointer.
There's one question in the chat by Alexander. Alexander, do you want to ask your question yourself?
Yeah, sure. In the example with the phantom stops, did every participant of this driving around the circle tried his best, or were there some kind of agents who actually brake on purpose?
I don't hope so. I mean, we have done the experiment, but I bet you if you would try to do the same and would really pay drivers, say 10 times more if they manage not to cause a traffic jam, even then most likely it would still happen. I'm pretty sure, because I know the mathematics of this. And we know that also from other kinds of phenomena, such as what they call the beer game, which is a logistics game, basically, where we have very similar phenomena. Are there any other questions in the chat? I don't see it, actually. All fine? Can we move on?
Yes.
All right, thanks for the question. Now here is another elementary pattern. It's basically a localized traffic jam that is moving and it's named accordingly. Here we have what we call stop and go waves. Note that they're basically progressing in parallel. That means with the same propagation speed, and that is an important thing to notice because that means there's some universal traffic constants. A little bit like the gravitational constant or the unity charge of electrons, and it's quite surprising that you would find such a thing in traffic flows, and it can actually be understood mathematically. Then there's oscillating congested traffic, and there's also homogeneous congested traffic, and that mostly happens after an accident or the closure of one or two lanes of the freeway. But now we're moving towards traffic flow modeling. And one of the first models developed is a fluid dynamic traffic model, and it's based on the continuity equation. So this is an equation for the density raw as a function of space and time is changed with time. And that is basically given by the spatial derivative of the flow. Does anybody have an idea why that is the case? Well, the continuity equation follows from the conservation of vehicles. So if no vehicle gets lost or is kind of emergent spontaneously on the road, which I've never seen in my life, then this conservation of the number of vehicles implies the continuity equation. And now we basically have to think how to specify the flow. And this is done over here through the so-called fundamental diagram. That means through flow density relationship Q of rho. And then basically you have a closed partial differential equation, and that can be solved. Unfortunately, it turns out that this equation has a tendency to develop some discontinuity. That means there are congestion fronts of so-called kinematic waves that form. The mathematics of this equation basically implies that the amplitude would not change, but the shape of the density pattern in space and time would change. And then you get those jam fronts and ends. This is basically the discontinuity that you see where the density changes abruptly. And that makes it pretty difficult actually to solve that equation numerically. And the phase diagram is basically this. So you have free traffic flow, and then above a certain traffic volume, basically you have congestion because there's a lack of capacity and vehicles just queue up, okay? However, as we have seen before, we have this phenomenon of spontaneously forming stop and go waves, right? And the Light-Wisdom model cannot describe such a thing. It can be described, however, by so-called car following models. And what you see over here is the Bandel-Sugiyama car following model, which is one of the simplest. So it basically has this acceleration equation over here, and it says that the speed of a vehicle is adjusted to a so-called optimal speed as a function of the distance between the vehicles, right? And then let's assume that we have such a, just for the sake of simplicity, of course it's not fully realistic, but we have this step function over here for the optimal velocity function. Now it turns out that traffic won't stay on that curve. Because of this adaptation process, we'll find an oscillatory process above a certain density threshold. And then eventually we'll find this trapezoid situation where speeds and distances change in an oscillatory way, in a very particular way. And that corresponds to the stop and go waves, actually. So this very simple model allows us to understand stop and go waves. It's not the most realistic, obviously, but it's good to understand the basics. So the emergence of stop and go waves is a result of the gradual adaptation of speeds. And so here we have again a trajectory plot. I think we show every fifth vehicle or so. And you see that in the beginning, there's almost equal distance between all the vehicles. But eventually, we see the emergence of those stop and go patterns. All of those waves are moving in parallel. And we have this traffic constant that I mentioned before. It's empirical, it's minus 15 kilometers an hour. So it moves against the direction of the road. Clearly, because in the traffic jam, cars are standing. They're moving out in the front, they're added in the back, so the entire thing moves backward, right? Minus 15 kilometers an hour is the traffic constant. And a little bit more realistic model is, for example, the so-called intelligent driver model, IDM. And it has an equation of motion and an acceleration equation below. And here you can see that this is an acceleration constant. This is the desired speed, could also be the speed limit. And here is a term which describes braking events. And that depends on the relative speed and the distance, but also the speed itself. And there's basically a desired distance, and that depends also on the relative velocity and so on. There's some time gaps and minimum distances in between. There's acceleration, deceleration, constants. And these kind of equations shown in a density plot will give you something similar to this. So again, we assume that we have basically constant density with very little variation. But over time, that very little variation will give rise to the stop and go waves that we see over here. By the way, we assume a circular road, so basically who moves out on one side moves in on the other side again, okay? Now, this is an overview picture of what actually happens as you change the density. So this is zero density, that is maximum density. And so for small densities, traffic flow is actually stable. That means even if you disturb it, it will go back into free traffic flow. For intermediate densities, or medium densities, I should perhaps say, we have linear instability, which means that the slightest deviation from the equilibrium value will lead to amplification effects, and we'll get unstable traffic and eventually stop and go waves, okay? Now, in between, what happens depends on the size of the perturbation. The further you go away from the instability area, the bigger need the perturbations to be in order to cause a traffic jam. But in principle, the two things can happen. Small perturbations will basically fade out, disappear, will have free traffic flow, but large perturbations will make your traffic flow break down. Same average density, right? So there's a history dependence, a hysteresis effect, a multi-stability, and that makes things particularly interesting. And that is actually the reason why we could have that kind of phenomenon. So the trick here is that we are in the so-called meta-stable regime, which is one of those areas where a finite amplitude determines or is needed to create unstable traffic. So this negative perturbation was actually, as we say, super critical. I mean, bigger than the necessary perturbation to cause a growing congestion pattern. And that's why this thing happens. Now, small perturbations just move on with the flow. That means forward. Large perturbations, we've heard, move backward because once cars are stopped, they're moving out of the traffic jam in front, and new ones, cars arrive in the back. So that the entire thing moves backward. Altogether, that gives us a so-called boomerang effect. And that's why the perturbation that already seemed to be having passed, or actually did pass the on-ramp, the inhomogeneity along the road, returns, and then it causes trouble, okay? Yeah, and the boomerang effect is actually quite frequent. We've seen it in many of our empirical traffic patterns, and we were interested basically to understand it better. Now, in the traffic simulations, it often appears that the amplitude is increasing, both when cars are moving forward and after the boomerang basically turned around. The second thing turns out to be true in the empirical data. The first thing, however, is not so clear. I mean, the amplitude doesn't seem to grow over here in the beginning as the jam moves forward. And that was kind of surprising to us, you know. So you see these things only if you look at the data very carefully. So most people perhaps didn't even care. And so we looked again at it in a different representation. So what you see over here is a freeway with 3 lanes and an on-ramp and an off-ramp down there. And then you can see we have these perturbations in the flow. Or here it's speed. On the other side is flow. And you can see that, yeah, the amplitude in the beginning doesn't grow, but the beginning of this perturbation moves with a constant speed. So it grows longer. While that happens, it grows longer and longer, and as it eventually comes close to that off-ramp, finally, traffic really breaks down, and then we have this growing peak on the other side, moving backward. Does anybody have an idea of what is going on here? No. Does anybody have an idea what speed this line corresponds to then? Just guess.
It says it's due to overtaking trucks. Is this maybe the speed limit for trucks?
Yeah, actually, this is true. 80 kilometers an hour. So what happens over here when one truck overtakes another one? Basically, the freeway is blocked. There is a blockage that moves with 80 kilometers an hour, and then cars arrive which move faster, and they would basically queue up behind those overtaking trucks. And that platoon of vehicles would grow bigger and bigger the more cars arrive, right? And this is what you see over here. And then basically, once cars are trying to move out of the freeway, that creates an additional perturbation, and that makes traffic break down. So yes, if you don't allow trucks to overtake during rush hours, then these kinds of effects are actually much less frequent. Okay, so here are the different congestion patterns again, the elementary ones that we talked about before. And these are to be understood with traffic models. And in fact, here you find simulated patterns that look similar to those that we have just seen before. Of course, the real patterns don't look as regular or perfect. But also those models over here are a lot simpler. They don't even distinguish cars and trucks. Of course, that can also be done, but to understand those congestion patterns, it turns out not to be necessary. So in other words, there's some traffic models that reproduce those elementary patterns, not all of them. So basically, different traffic models may produce different patterns. And some of them will be able to match those that are actually found empirical, and some of them not. And then perhaps one shouldn't call them traffic models, but anyway. So the question is, how well do these kind of models actually allow us to understand what is going on our freeways? And so we have been looking into empirical data. It was quite an effort at that time, you know, even to get access to data was a pain. But eventually we managed, and what you see over here is that there's in fact some regularity. So the moving localized clusters, M, are in a certain corner of the plot. Free traffic flow goes up to here, but there's overlaid congested traffic. Pink localized clusters over here, stop and go ways over there, oscillating congested traffic over there. And now, if one also considers that the outflow from congestion, which is also a typical traffic constant in principle, namely about 1,800 vehicles per hour and lane. This so-called traffic constant, however, still depends on the weather conditions, right? Most models don't consider weather, but so there's a difference between data and models in many cases. But considering this dependence on weather, we can basically rescale the flows. And if we do that, then suddenly the empirical pattern of the diagram of the congestion patterns looks a lot more ordered. So we have a very clear picture, in fact. And this turns out to be actually well compatible with what we call phase diagrams of certain kind of models. Now, the phase diagrams depend on the kind of model. Scientists came up with probably hundreds of traffic models, what they thought were traffic models. And they produce different kind of collective patterns, congestion patterns, right? But each one might have different characteristics. And those characteristics are basically represented by a so-called phase diagram that shows what kind of outcome you have as a function of the upstream traffic flow and the bottleneck strengths. And this could be actually the on-ramp flow, and it's a flow of cars entering the freeway. So the sum of both would correspond to the overall traffic volume downstream of the on-ramp. So those diagonal lines basically correspond to the same traffic volume downstream of the on-ramp. So for little traffic volume, we have free traffic. For large traffic volume, we have congested traffic. This is what you expect. Now, if you have more sophisticated traffic models than the Light-to-Wisdom model that we had in the beginning, then you could also have additional phases that would, for example, contain oscillating congested traffic or stop-and-go waves. And how the phase diagram looks like depends actually on the fundamental diagram. And actually, not only the fundamental diagram, which is thus this flow density curve, but also the instability points. So the point where the metastable density area sets in, the point where we enter the linear instability area, the point where that ends, and we enter again the metastable regime, and the point where that again ends. And there are flows corresponding to those densities, those so-called critical densities, and the relative positions and the sizes of those flows basically determine the fundamental diagrams that you get. And there are situations where the traffic pattern might be history dependent, as I mentioned before. Small perturbations would cause a different outcome than large perturbations. That means you could either have free traffic flow or congestion. Congestion for large perturbations, free traffic flow for small perturbations. And that makes things complicated, but complicated means interesting for a scientist. But for the engineer, it's also interesting because, well, where you often have congestion, you could in principle have free traffic flow. Obviously not everywhere, but all those areas which are overlapping with free traffic could be turned into free traffic with some piece of technology. Right, so do you understand why it's important to have these phase diagrams? Because they deliver insights into how the system behaves, under what traffic flow conditions, and why. And that basically delivers us some new solutions, okay? Now also, you can basically classify different traffic models according to the phase diagrams that they produce. And then you would choose that class of traffic models that has a phase diagram which corresponds to the empirical phase diagram, okay?
Dirk, there's one question about,
okay, good, please, good.
I think it was in the previous slides. What does M, P, S, and O means?
M is the moving localized clusters, P is the pinned localized cluster, O is the oscillatory congested traffic, and S is the stop and go wave. And There's also H in some plots, and that is the homogeneous congested traffic. Okay. Here we can see congestion patterns, and particularly how extended the congestion actually is as a function of time. The white lines correspond actually to what is predicted by the traffic models. So the nice thing is, once we know when congestion started, and that is something that was probabilistic, as I said to you before, because it may depend on a single overtaking maneuver of two trucks. But once it started, we can basically calculate quite well the extension of the traffic congestion and also the delay time that this will cause. Which means that we have actually gained a very good understanding of what is happening on our freeways, even though we've seen those complex patterns in the beginning that look pretty hopeless to understand. But by breaking it down into those elementary traffic patterns, it was actually possible to understand it, to model it, and also to make some predictions. And I think the take-home messages you can read at home. And now we have actually applied this insight in order to come up with new kinds of adaptive cruise control systems. These are systems that are based on, for example, a radar sensor or a laser sensor that measures relative velocity and distance of cars, and would let the car automatically accelerate or decelerate, right? And the cars could try to mimic the behavior of real drivers, or they could change the behavior of acceleration and deceleration a bit. And this is what we have actually done in order to dissolve traffic jams. Now, cars, of course, are getting smarter and smarter. We've done that kind of work many years back with a big car company. That was in 2007, where I think nobody almost was talking about Google Cars at that time. We were already working on board data acquisition, what we could call perception, inter-vehicle communication, on cooperative traffic state determination, something that we might call cognition or something similar. Adaptive choice of driving strategy, could call that perhaps decision making, and drivers would be informed and traffic assistance would be given. And in many cases, you would basically have cars accelerate and decelerate autonomously. And the left car is according to our adaptive cruise control system. The right car is the one that other units of the car company produced. And they were actually more satisfied with our own approach, which was adapting a bit better to changes of the behavior of the car in front. But most importantly, I mean, the main effect was that it was not only more comfortable for the driver because the car was driving for them, but we've also developed that system in a way that we would have cooperative effects. The traffic flow, in fact, would be stabilized using different kind of data. But most importantly, we have stabilized the traffic flow by changing the parameters in this equation. Not dramatically, so it feels still very natural what the car does as compared to what the driver would do. But those constants A, B, T, they're being changed. So in free traffic flow, we basically try to imitate what the driver would do. But then when the upstream end of congestion is approached, the deceleration constant is being multiplied with a factor of always 7 over here. And then eventually we'll drive in the congested traffic area. Then comes driving in the bottleneck section, and eventually you arrive at the downstream end of the congestion. And here, most importantly, cars accelerate more forcefully. This is important for the sake of stability. And at the same time, the time gap is reduced, which is important to have an increased capacity. So this taken together basically changes the outcome of collective traffic flow patterns. What we're doing here is we're first simulating stop and go traffic as we find it actually in reality. I've seen that many times, I guess. And this is just to illustrate that the models basically reproduce realistic driving behavior quite reasonably. And now to see the reason for that traffic jam or stop and go traffic, we take a helicopter, and now we see an on-ramp actually, where cars are trying to get into the freeway, and that produces small perturbations that are being amplified, as we discussed it before, and that produces a stop and go traffic flow. However, we'll now turn on in a few seconds the adaptive cruise control system, or traffic assistance system, VLA, that accelerates and decelerates slightly differently, as I said before. And as you can see over here, the traffic flow is stabilized and the traffic jam is dissolved, even though the same number of vehicles is entering the road. So now basically the road can handle a higher number of vehicles without additional road capacity. I mean, without additional lanes, right? Just by changing the interactions between the cars. So basically, what made this miracle happen was not a traffic control center that was trying to control every single car, but a real-time measurement and feedback that changed the interactions of cars in such a way that a different self-organization effect would result and different collective pattern would come out, because we've seen before there are different kinds of traffic states. And basically, to some extent, you can change what traffic state would result. And of course, you're interested to have less congestion and, if possible, free traffic flow.
Dirk, there are a couple of questions in the chat.
Yes, please.
First one is VLA activated for all vehicles?
That is extremely interesting. It's not necessary that all the vehicles are equipped with that kind of technology. So if there's 30–40% of vehicles doing this, it would already have this dissolution of the congestion effect. And I think that is particularly unexpected and interesting. In fact, you're seeing it on the next slide. So what I'm trying to see here, we're now living in the Internet of Things age, where it's cheap to measure what different components of the systems do. And this allows us basically to build a new kind of control approaches. We can make the invisible hand work, basically, the self-organization work for us. So here you can see actually how the outcome changes with the percentage of equipped vehicles. Even if there's only 10% of equipped vehicles, the congestion pattern would be much less severe. And with 20% equipped vehicles, already it's almost disappeared. Now, it's important to know that small changes in capacity would actually have potentially dramatic effects on the delay times. So a little bit of improvement in terms of the capacity has really very favorable impacts on travel times. And now, of course, you need to know where the fronts of the gems are in order to adapt your driving parameters accordingly. And every equipped car would actually measure data, and that kind of data would then be transmitted to other cars with that piece of technology. And if in the beginning, if only a few cars have that technology, it's actually difficult to transmit that data and to make that collective favorable pattern work. But then if you transport data using vehicles coming the opposite way on the other lanes, then actually it turns out that a very small equipment grade, like say, I think it was about 3% of equipment would already allow that communication system to work. But only if cars help each other. That means we carry on information from the opposite flow direction. But of course, that can be programmed in, okay? So in this way, we get that information about where the traffic jams are located. So we can adjust the parameters accordingly, and we can dissolve traffic flow. Any further questions right now?
There was another question by Samuel. It was about, is it impossible for human drivers to learn this type of driving? I think it was for the previous.
I think to some extent you can learn it, but even experienced drivers have their limits. And this is basically because our human senses have not been evolved for traffic flow. So it's very difficult to really determine the exact distance between two cars and the exact relative velocity. It's an estimate that people have. And technology can measure that more precisely. And reaction times can be reduced. And that can be used basically to come up with a more favorable organization. I'm not talking here about brute force platoon control in a centralized way that some other research teams have also been looking into. I'm not so convinced of that personally, but okay, I mean, people are trying that too. All right, let's move on to cities then. And of course, traffic planning has noble goals. We want to have better mobility. We want to have less pollution. We want to have less noise, less traffic. But the reality is often this, right? A lot of congestion and urban gridlock. And the question is, does it have to be like this? We've been inspired a bit actually by how the cells in a human body work. And each cell does have a center, a nucleus, and they have transportation, what should I say, so-called filaments that are a little bit too similar to train tracks or roads along which vesicles that correspond to the vehicles would transport certain kind of substances inside. Okay, these are those units over here. These are the vesicles. And it turns out that actually those vesicles, they don't produce congestion. And this was very puzzling to us. But in fact, if there was congestion, it would be like a terrible disease. So our cells have learned to avoid congestion. And that was inspiring to us, and we thought, okay, maybe we have to reinvent the way to control traffic lights. And today we have traffic light control centers that are collecting as much data as possible about the traffic situation and trying to come up with an optimal control plan and then to impose it on the city and in this way control traffic flows too. But it turns out it's a so-called NP-hard optimization problem. That means the computer power needed grows more than polynomially with the size of the city, and there are so many parameter combinations that are possible for each traffic lights and for two traffic lights, and even more so for more traffic lights, that basically there is a really explosive complexity, and you can overwhelm every supercomputer basically with a medium-sized, even more so by a large city. And so traffic optimization cannot be done in real time exactly. You need to make simplifications basically, and the approach is basically that you're trying to come up with cyclical, periodic operation and to synchronize the cycles. That is the typical approach. And then you try to come up with perfect synchronization, optimal synchronization pattern, and to impose that. But it turns out that this is an optimal solution for a traffic situation which almost never occurs. We instead wanted to have an adaptive traffic light control, which would perhaps not even try to do the come up with 100% best solution, but to have a solution that is adapting to the real traffic condition locally and doing a short-term prediction considering the inflows into the road sections. We want to have something which can adapt to complex street networks and to traffic disruptions, such as building sites and accidents, or particular events such as Olympic Games or pop concerts and so on. We had to basically model those systems. And of course, you abstract the road network by a mathematical graph. You'd have to overlay the traffic dynamics, and here one could actually use a Lytle-Wissam model, the partial differential equation introduced before. And are basically two characteristic velocities. One is the speed limit, and the other one is this propagation speed of jam front is the minus 15 kilometers an hour. That's the smaller case c here. This is the location of the traffic light. Here it's red. Once you turn it green, then eventually cars accelerate. We assume it doesn't take much time to accelerate. That's why you have the straight lines. Okay. Jam front moves backwards as expected. And that's also what you basically find. So now it turns green and we'll see the jam front move backwards. Okay, as we just had that in the graph. Those partial differential equations can actually be transformed for a triangular fundamental diagram into a delay differential equation. So everything that happens in the road section is basically determined by the inflows and by the outflows. That really simplifies things dramatically. A very interesting thing, I would say. And so even the jam front and where the location is determined by the inflows, arrival flows, and the outflows and departure flows. Okay. Also, the delay time can be determined by such a delay differential equation. I really love this equation. Now, I used to be a theoretical physicist, and here also we have conservation of flow. No cars are being lost or left behind. What flows in flows out, like the Kirchhoff law in a sense. And then you basically have to specify what happens if you connect two road sections. We have different numbers of lanes, for example. What happens if you have a diverge? What happens if you have a merge or an intersection? You can see, okay, these equations look a little bit difficult. But the most interesting thing about those equations is that there are those minimum functions in there. And that corresponds to the capacity drop, right? So basically, the goal must be to avoid the activation of the minimum function, that means to avoid the capacity drop. I imagine that you have a system of many such equations that are coupled with each other. How difficult would it really be to avoid those capacity drops? You can imagine really that you can make a lot of mistakes on how you control the flows. It means your capacity of the road network really depends on how many of those minimum functions are switched on or off. And this does not have directly something to do with the traffic lights. Of course, it has to do something with them, but things are more tricky. So here is an illustration why you have that minimum function. So as you can see over here, there's a diverge. Now the road is full, and also this straight flow over here has been stopped, basically, right? That's when the minimum function was activated. I think it's clear what the problem is. Then each of those intersections might have different features, numbers of lanes. Do you have separate lanes for turning left and turning right and going straight, or do you have shared lanes and so on? So this is just one kind of intersection. It's already represented by a pretty difficult graph. And as I said, many intersections could be different, and all of those are then connected to each other. So it's really becoming a pretty messy graph. But today, at least the data is available, and you can read it from a DVD-ROM or from just a database, and you can code an entire city as a master student, while before you may have needed actually 50 PhD students or so, to produce a simulation of an entire city. So yeah, availability of data has really changed things dramatically. Now we have to take into account also the traffic lights, and we do that by introducing a prefactor to the maximum flow. That was the 1,800 vehicles per hour in lane, typically. And so when there's a red light, G is 0. When there's a green light, G is 1. Okay. And that's about it. And then you can start basically simulating flows. And the next thing is how to switch the traffic lights. And here, 2 of them only. And what we want to have is basically a system that produces a green wave. That means cars that pass one traffic light would pass another one without stopping, and perhaps even more. But you can do a lot of things wrong. There could be non-optimal phase shifts, there could be different cycle times, there could be stochastic switching, and so on. Now, we'll accelerate things a bit. It's also funny to talk about this, but it's not that important. And what those slides basically wanted to say. There are different kind of situations you can have or faces. But the most important thing is that we have actually tried to come up with a new paradigm. One which was going away from regulation or over-regulation to self-organization. That means approaches that would support the formation of coordinated traffic flows. And this was very much inspired also by an observation that I made in Egypt, close to the Giza pyramids. And you can see over here, there's no traffic light, there's no policeman, and there is no congestion. Highly diverse traffic flow. Almost nobody is stopped. And this magic happens because of the particular road design. They have, or intersection design, they have a unidirectional flow in front. In the back, they have the opposite unidirectional flow. And most importantly, they have some buffer in between, which allows every traffic participant to adjust the speed in such a way that they would find a gap in the flow when they need one. Of course, there's a lot of honking that you don't hear, and modern traffic organization would like to do the same wonderful self-organized traffic organization without much noise. And that can be done with the Internet of Things in principle. Now, we've also been inspired by what we'll see in our next lecture, the self-organized oscillations of flows at bottlenecks. And these are simulated pedestrians. You can see there's a flow back and forth, even though there's no traffic light producing those oscillations. There's also no policeman or something. So the idea was we could actually come up with a pressure principle that would produce self-organized oscillations and use that to define traffic lights. So the traffic flows would control the traffic lights rather than the other way around in a bottom-up way. So you have sensors that measure the outflows and the inflows to the sections, and the inflow measurement allows us short-term prediction and allows us a coordination of neighboring traffic lights in a very adaptive way, as you can see over here. And what comes out is many green waves, as we like it. That is, of course, for a Manhattan system, or also we have that in Barcelona and other cities. And the question, how well would it work in reality? And also compared to different kind of traffic organizations. So basically what we have done is we have compared 3 different ways of controlling traffic flow. Of course, the traffic control center was one of them. Here, the idea was we have the center act like a benevolent dictator, is trying to come up with the best possible coordination of traffic flow, but it needs to approximate, right? And it typically has these repetitive patterns. It does not in each minute come up with a different kind of traffic organization. Here, we have every intersection decide traffic lights by themselves in response to what happens in the neighboring road sections. We have the bottom-up self-organization. Each intersection is trying to do its best, but there's no coordination between the neighboring intersections. It basically corresponds to each intersection acting like Homo economicus, right? Trying to do travel time minimization. Everyone does the best, but nobody cares about others. So we would expect that couldn't be as good as the centrally controlled traffic flow. And here the third one is basically doing the same thing as the second, but if there are long queues, we would first clear the queues in order to avoid spillover effects. That is favorable to the neighboring sections, so we call that other regarding coordination with the neighbors. Before we go back to the travel time minimization. And so, as this is so friendly and make compromises in a sense, we would think that would probably be the worst organization of the traffic system. Let's look what really happens. Red curve is for top-down regulation. We see the queue lengths of cars at an intersection as a function of the capacity utilization. And we see basically a linear increase as the traffic volume increases, the queue length increases. Okay, makes sense. Nothing unexpected. What is interesting, however, if we have this selfish optimization, a homo economicus approach, we have much shorter queue lengths for low capacity utilization. Because, there's not a periodic service. So basically at low flows, whenever a vehicle arrives, it will be given a green light adaptively. And so that works better than the periodic service approach. But there is a point of capacity utilization where suddenly things go wrong and the queue length explodes. And then, of course, the traffic center says, hey, yes, that's actually why you have us. So we can say that here, for low capacity utilization, Adam Smith's invisible hand works. The self-organization is better. But there is an area where actually it fails, and where the centralized coordination and control is needed, it seems. But surprisingly, the third approach, this other regarding optimization, that takes care of neighboring intersection, and that is doing better all the way. So here we have basically a combination of the travel time minimization with the clearing of long queues, right? So we can make the invisible hand work. Interestingly, by a combination of two mechanisms that separately fail to improve the traffic situation. And this is quite unexpected, I would say. You see, in fact, there is a different kind of organization. This is still for a single intersection. So if you have a regular inflow, it could happen that one road section will get served twice, while another road section will be served once in a cycle. So suddenly there are new service patterns that come about in adaptive ways. But as I said, it's improving actually the performance. That's good for everyone. So yeah, we compare self-control with kind of classical control approaches, and actually the queues tend to be shorter. I think you can see that slightly. And of course, we have to make a quantitative comparison. And it turns out if you have not a constant inflow into this intersection, but variability of the inflow, then the combined program, which this is the third one, the other regarding self-regulation, that is actually working even better than the fixed time control when there's a lot of variability. Then the question is, what happens if you have an arterial with many intersections? And if those intersections may have even different distances from each other, which really messes up things. In particular, if the flows in both directions are quite different. And it turns out, actually, also, again, there's a huge improvement by the combined controller. So somehow it manages to coordinate flows nicely because of this adaptiveness that I talked about, the that considers short-term prediction of arrivals of vehicles. In fact, on the left, you see the classical green waves, where you impose a certain flow pattern in one direction, say out of the city or into the city, but not both ways. So if you go the opposite direction, you don't have a green wave. Rather, actually, you're being stopped many times, as you can see over here. Our combined controller doesn't have that broad green wave bands, but it's much more usable in both directions. So there's a lot more adaptiveness in terms of how gaps in the flows are being used. And we observed that also for road networks. Again, the combined approach is much better. And goes so far that even if there is an accident, things are managed in a much better way. So here the road blocking happens. And on the top, we have the consideration of long queues. And we avoid that road intersections are blocked, while below is what happens in, I guess, most cities of the world. And things get totally blocked and you have a huge, huge mess that spreads very quickly. Now the question is, how does it really work in real life? And so we've been talking to the traffic authorities in Dresden, where I worked at that time. And they said altogether they were happy with the system that they had. I think it cost several millions. It was a state-of-the-art traffic control system that produced green waves and even adaptive green waves. But there was one issue, which was they had a lot of, first of all, a very irregular road network, but also on top of that, many trams and buses that were cutting through this area. Different routes are taken even. And they wanted to prioritize public transportation. And if they did that, basically it destroyed the green waves, and that created monster traffic jams within a short time, so they couldn't prioritize public transportation. They said, okay, if you think you're smart, then take this, you know? And in fact, Stefan Lemmer, who was my PhD student at that time, is still working in this area now, is implementing this control in reality. He was working on that, and he was actually coming up with a solution that worked better. And this is just a visualization, so I'll skip. It's much more meaningful to look at these graphs. So on the top, you see the classical green waves produced by the system that they had. On the bottom, you see the more flexible self-control of our system. It doesn't have the broad green wave bands, but it's a lot more adaptive to the real traffic flows, okay? And as a result, it was possible to prioritize public transportation, but nobody had to suffer for that. So the cars did also have even improved service, and more so, even the pedestrians and the cyclists. And for the environment, it was better too. So basically everyone benefited. It's more green for everyone was basically the headline that you could recently read in the newspaper. So this is amazing, and it's based on this new approach, the bottom-up self-organization, where local coordination spreads throughout the system if you have the right kind of interactions in the system. It's the interactions that matter for the outcome of self-organization. It could be terrible self-organization, but if you have the interactions right, which is kind of the tricky thing, you know, the challenge, the scientific challenge. If you have the interactions right, then you will have wonderfully adaptive and coordinated systems. And I see we're at the end of the lecture, time-wise, but also content-wise. And so basically we're concluding that there are basically limits to centralized control. Centralized control works in many cases quite well, but not so well in complex systems with heterogeneous elements, large degree of fluctuation, short-term predictability, and then greater flexibility to local conditions would often perform better. So the higher the complexity of the system, if you want to achieve a high level of your goal function, then you need to give more autonomy of control. That is basically what the conclusion is. And again, there's some take-home messages that you can read at home, and there's a lot of literature that you can also have a look at. Are there any questions or comments?
There's one question. It's about, are roundabouts better than traffic lights?
That's a good question. Actually, yes and no. It sounds like the answer of a lawyer, but not quite so. Roundabouts work very well for small and medium level traffic volumes. If you have high traffic volumes, however, they're reaching their limits, and then you need to have traffic lights to support the coordination. But in fact, many intersections that are now controlled by traffic lights can actually be replaced very well and even better by roundabouts. And that's why you see more and more of them. I think one more question, right? Can you read it to me?
Yes, it says, how hard is it to implement these adaptive solutions? Is it easy to apply for any situation?
I think it really has a lot of advantages. It can be fit into existing systems, can replace, say, the control of single intersections. You can, of course, also do it for the entire city. You can do it for, I think, cities where you don't have such a big budget. You don't have to use necessarily sensors that are below the road surface and cables that connect those sensors with the traffic control center. Instead, you could have local sensors and perhaps wireless communication locally. As everything is local, you can save a lot of money, I think, potentially. And so that is an additional benefit. It has benefits for traffic participants, it benefits for nature, environment, and has benefits for your budget as a city, I think. And so it's, we're not, if the question was, is it scalable? I think in principle, yes, but it's not yet something like a franchise system, you know. If that was your question, but I think you could, in principle, do that.
Or also, for example, do you need a master student to program it? Or is it a standard piece of software you can distribute anywhere?
I mean, it's not yet plug and play in the sense like, you know, you have your traffic network implemented, and you have some data about the inflows, route, origin, destination, matrices, or whatever. And then you push an additional button, you have all the traffic lights ready. We are not yet at that point, but you know, I could very well imagine that a smart PhD student could get it to that point. And in fact, we are working on this right now in some of our traffic projects. So we're now combining this analytical approach that is using mathematical formulas for the short-term prediction and so on. We're now combining that with machine learning. And it's actually better than machine learning alone. So this is really interesting. But yeah, combining the two things would perhaps also help to kind of automate the setup for larger areas of cities. Yeah, I mean, if you want to make a master's thesis on that, I don't know what you're studying and what semester you're in, but yeah, there's a lot of interesting stuff still to be done.
There's one more question. It's like, would an increase in speed limit within cities be a legitimate measure to speed up traffic? Example from 50 to 70?
The effect of speed limits on the overall capacity is non-trivial. I remember that on freeways, you could have a situation where reducing the speed limit could actually improve the traffic situation, in particular reduce congestion. That had something to do with heterogeneity in the traffic flow. If cars were not so much faster than trucks, there were less perturbations, less large perturbations that were those that were triggering breakdowns of traffic flows, right? So the capacity drops. So you made traffic more homogeneous, and you could do that also with, again, adaptive traffic control systems, including adaptive traffic light controls, like on-ramp controls, for example, to homogenize traffic flow. I don't know exactly how the situation is for urban traffic flow, what the models predict for changing speed limits from 50 to 70 or to 30. I could imagine that you could have interesting counterintuitive effect, that sometimes you have a faster or slower effect. That could potentially happen in particular in network systems such as urban traffic flow systems. So sometimes more speed makes coordination more difficult, and that could create more trouble, but perhaps not always so. It's, I mean, as I said, traffic flow systems are really very interesting because they do show often unexpected effects, and you get excited about that, I guess. I hope. That's what I do. All right, anything more?
Just more of a general question.
Yeah.
We had the example of the on-ramp for the highway. I mean, in this particular case, we assumed that like the people that or the drivers are already on the highway would slow down. But I mean, you could also consider that people, for example, would speed up in order to let the cars on the on-ramp enter the highway. So it kind of depend on how cooperative people are, or the drivers are, or how rule following they are, on what kind of models you get.
Right. So I think many people, of course, have this idea that why doesn't traffic flow the way water flows? You know, so if you reduce the cross section of a water pipe, then the water flows faster, and basically the continuity equation enforces that. And so you don't have congestion in a water pipe as we have it on the road. So couldn't cars go this way? And the answer is not really, because first of all, they have a lot more extension compared to a water molecule. And then also there's this desire to feel safe, right? You wouldn't want to have a very low distance at very high speed. Maybe with the exception that the cars have exactly the same speed, but still, you know, you need to merge cars, you need to. So if kind of a platoon of cars drives like a train, then perhaps you could imagine that low distances at high speed would be possible, but I do have a little bit of skepticism with regard to this, because people may not feel comfortable and safe, and that is what also matters. People are people and not particles. Yeah.
That's true, but at the same time, for example, I'm more of a defensive driver. I don't think I would, don't feel very comfortable, for example, on an Italian highway, because people tend to be more aggressive.
Right.
So, but at the same time, wouldn't more defensive drive style in certain circumstances cause or have a higher probability of causing a congestion?
Well, if it produces inhomogeneity, yes. I mean, these local perturbations. It is really an interesting question also, you know, would really purely autonomous traffic increase the traffic capacity significantly? And I can see that, okay, for the platooning systems, but their implementation is perhaps the less likely and the most difficult ones. While if the cars would be automated, they would have to follow today's traffic rules, which include like you need to have a time gap, I think, around 1.8 or so seconds. Then it would probably turn out that automated traffic would have less capacity, because in many cases, real drivers actually drive at much, sometimes significantly reduced time gaps, in particular if there's rush hour. So drivers are surprisingly adaptive also in their driving styles. And they're not doing that badly. Yes, they're making sometimes mistakes because of the complexity, and they're tired, but I think also the complexity is overall underestimated by those autonomous driving concepts. So can you really perform a lot better with less intelligence? Or do you need to basically build human intelligence level AI into cars to take over traffic altogether? We'll see. I mean, just remember that basically we should have already automated traffic on the streets for at least 2 years. That was the prediction, and it hasn't happened. So a lot more challenging than people thought, because I do think a lot of the engineers don't know enough about self-organization and don't know enough about complex systems, first of all, and how small deviations might actually amplify and cause instabilities and all sorts of trouble. So my approach is not to fight complexity, but to learn how it behaves and to use that behavior of complex systems to our favor. So complexity is not the enemy, you just need to learn how to use it. And then you get those basically the very nice, self-organized, coordinated, efficient, and adaptive and resilient organization of traffic flows.